Hello and welcome back. Now I want to look at refraction. Imagine that we have a surface, which I'll denote S. This could be flat or curved, it doesn't matter, but locally at least it'll look flat. There'll be some normal vector protruding out from a point which a ray has intersected, and if we were to trace that inwards, the normal vector would extend into the surface as well. We have some incident ray, a little dodgy on the drawing, but here it is, which intersects that surface at some angle to the normal, and then it passes through the surface to give a refracted ray, which again has some angle, which is different. What I'll do is just denote we have the incident angle and the refracted angle, and the two mediums that we're crossing between have different refractive indices. There will be some refractive index in the incident medium that we're traveling from, and some refractive index in the medium that we're refracting into. So far, so good. As well as this, we also have Snell's law, which states that we have the following relationship. If we have a vector, say v, then that vector can be written or decomposed in terms of some sort of reference vector. For simplicity's sake, it can be in any direction, but we're always going to assume that it is emanating from the origin of v. So here's how we break it down. Any vector v can be referenced or can be decomposed in reference to any vector u, and it decomposes into a vector sum. So there'll be a component of v which is parallel to u, and there will be a component of v which is perpendicular to u. And so what we've got is, because we know v and u, we can get the parallel component. So we'll say the parallel component of v and u is also denoted as the projection of the vector v onto the vector u. It is a copy of v which is stretching out, it's parallel to u, so it is a multiple of u. Let me just butt in for a second. I know that as I talk through this, I'm sort of repeating myself a little bit, but the aim here is to enrich the understanding of these concepts so that not only can you solve this problem, but later on when you see a vector problem, you can break it down and reason about it. So bear with me. If you're already familiar with linear algebra and these concepts, just sit back, sip your coffee. This is light entertainment. Anyway, so what I'll need to do is I'll need to say, well, have some angle, and the length here will be the length of v times the cosine of the angle, which looks a lot like the inner product, especially if u is normalized. So what we'll do is I'll take the inner product of u and v. In order to normalize that, I'll divide by the magnitude of, and then I want this to, so at this point we've bounced it down to a number. It's simply a number that indicates the length of this vector. In order to orient it in the direction of u, I then need to multiply it by normalized u. But then, if we look at normalized u will be u divided by its own magnitude. And then if we look at these denominators, they'll come in together and we'll have magnitude of u squared on the bottom. But as you may be familiar, the magnitude of a vector squared is really the inner product of that vector with itself. So that is the formula for v parallel to u. Now, in order to get v perpendicular to u, we could go through some more complicated math, or we could simply use the fact that if I take the vector v and subtract from it everything that's parallel, what I'm left with has to be everything that's perpendicular. Okay, so with that in mind, what I'm getting at is we can decompose these vectors with reference to the surface. So I'll break this down. We'll have The incident vector will have some component which is parallel to the surface that we're shooting into, and some component which is perpendicular to the surface. And the refracted ray, likewise, will have some component which is parallel to the surface, and some component perpendicular to the surface. For simplicity, I'm going to assume that all of these refracted rays, incident rays, and the normal are all pure direction vectors. That is to say, they have a magnitude of 1. If we remember Snell's law, which I wrote just a second ago, one big thing we had here was sine of the angle, because we know, okay, so these things we know the refractive indices, we can pretty much work out, because we know what our incident ray and our normal is, we can work out what the direction there is. The thing that we need to solve for is the unknown angle. So just to help with things, I'm going to look at some quantities. With sine theta I, these vector decompositions are orthogonal. They're right-angled triangles. The component parallel is orthogonal to the component perpendicular. And so we look here, we have opposite side, so the length of I parallel, divide by the hypotenuse, which is the length of I, which is really just the length. I'm just going to write I parallel. And likewise, if we look at this case down here, we have additionally, we know that all of these vectors are actually going to be parallel to each other, if that makes sense. So this I parallel is also parallel to the surface, is also parallel to R parallel. And the same goes for the perpendicular vectors. So for two vectors to be parallel, that means that one is a scalar multiple of the other. And so we have some multiple of I parallel. Okay. And if we take these facts and put them into Snell's law, we can see that the magnitudes are related by this scalar multiple, and therefore that tells me that the parallel vector is NI/NR times the parallel incident. So let's have a look at the parallel vector. So what I need to do is I need to get a handy expression for this vector here in terms of the information I have in this diagram. Remember, I know my incident and I know my normal. And then furthermore, if I look at this diagram here, if I take, so I'll say, if I take the length and multiply it by cosine, but then I'll have to also multiply by the normal, this is getting a little funky. What I'm getting at, there's also a negative sign here. I'm sorry, this is a little messy, but let me try to explain my reasoning. What I'm saying is, yeah, I is coming in this way, but imagine I was coming out the other way. That's negative I, that's why I'm putting that negative multiplier out the front. Now if I take the length of that vector, cosine with n, okay, great, that's the projection of I onto n, that's telling me how long I is parallel with n, and then multiply it by n, n's already a unit vector, and so we have got, oh, we also know that I is a length of 1, so this comes out to negative cosine theta I times the n vector. Great. And then remember that I parallel is I minus I perpendicular. So I've got I minus this thing which has a negative, so plus. Okay, so I've got a nice expression for R, but really my goal is not to get R parallel, but to get R. That'll be the refracted parallel plus refracted perpendicular. And so what I'm going to do is I'm going to sort of recast this a little bit. So we have this vector equation, and now I'm going to get things in terms of length. Because these vectors form a right-angled triangle, we can apply the standard quadrature rules and then take the square root of both sides. So inside here we know the length of refracted is 1. And so we can use that information because we know the length of the vector to basically find its vector equation. We know it's going to point in the direction of the normal. So I'll multiply it by n. This is outside of the square root here. But also it's going to be in the direction of the negative normal. So we have the positive normal upwards, the negative normal will be downwards, and that's why I'll put in that minus there. And so if we look at this, we have an expression for the parallel component of the refracted ray. We have an expression for the perpendicular component of the refracted ray. Maybe I should use this one down here. That's better than the one above. So let's put this all together. So I'm going to have to flip over to another page. So if we look at this really carefully, we can see that there's a component here which has no reliance on the normal, and then there are these components here which do rely on the normal. So I'm going to factor that out a little bit. We've got this expression, almost everything we know here. The last thing we need to evaluate is the length of this refracted parallel component, but if we look back to the diagram, we found that the length is equal to sine of the refracted angle. And furthermore, we have a relationship between the refracted angle and this. So if I go back, I'll say, so again, all of this stuff we know so far. All of this stuff we know so far, remembering that this cosine expression is, if we were to take the negative I dot with n, both of which we know, so we'll go negative I dot n, okay, we have an expression for that, that's fine, and then minus this thing. Okay, so everything here we know, it's just this part in here, we know that sine theta, this expression here. So this gives us that expression there. And then furthermore, if we look at this, this is really 1 minus cosine squared. So if we know cosine by this expression, we can also get cosine squared. And in a roundabout way, we can do it. Now, hopefully, GLSL has its own refract function. All right, editing Andrew from the future here. I know this derivation may seem a little long-winded. Turns out that GLSL does in fact have a refract function, and thankfully, it's operating the same way as I've presented here in my work. So what we do here is we take in the incident ray, we take in the normal vector, and this eta is the ratio of those two refractive indices. I call them n because they look like n, let's be honest, but the Greek letter there is eta. Now if I pop down to the formula that we use, I'll just superimpose this against what I've written. I've got this k value, and this k value here is what's happening in that square root. So we have 1 minus the eta ratio squared, and then times, and then here, anytime we see dot ni, that is the inner product between the normal and the incident. And so the dot there will be the cosine theta, basically. So cosine theta squared, okay. Now if we have an eta value less than 0, we have what's called total internal reflection? Forget. Anyway, it's just not going to be solvable, basically. Otherwise, the refracted ray, this R is what's going to be returned. So we have eta ratio times I minus, in here we have eta ratio times cos theta plus the square root times n. So I just wanted to pop that up because I do find it satisfying when things actually work. But I just wanted to go through the math there. I know this is far overblown explanation, but I hope that seeing it makes you more confident dealing with life, really. Okay, so that'll be it. Let's have a look at that in action. That's the derivation of the refraction formula. The next question is, how are we going to deal with this in our code? Here's a sphere. As always, we'll shoot a ray. That ray will intersect the sphere, and there will be some surface normal at that intersection point. In the previous video, we were dealing with reflections. So let's go ahead and add one of those. And there will also be a refraction. A little messy, but there it is. So here's the situation. The way our code currently stands, we can't really spawn two true rays. Otherwise, it's a geometric explosion of complexity. So first of all, we'll have this ray has come through and traced against the whole world. It's the true ray trace. And then this refracted ray will continue and rebound and be tested against the rest of the world. However, this reflection ray, as a quick approximation, will actually only be tested against the sky. So if this ray were to actually would probably reflect other spheres, they won't show up. We'll just have a reflection of the sky on the surface. In the previous video, we were also dealing with reflectance. We had a reflectance variable which was tinted every time it interacted with the surface. Now, instead of a reflectance variable, I'm going to have energy. And the difference is energy will sort of track the color of the ray. So if the ray hasn't hit anything by this point, then you can think of it as a white ray. It's completely white. And then if this sphere is red, well then this ray here will be red because it's traveling through the sphere, it's transmitting, it's picking up that color, and this rebound ray will be white still. But as we can see, currently this is not energy conserving. Have some amount of energy and it doubles. So in order to track that, to conserve that energy, the sphere also has a reflectance parameter. So we'll say reflectance times energy will be the color modifier for this ray, and this will be added onto the result original ray because it's a reflection. And then for this ray here, this ray will not directly additively contribute, but what will happen is the ray will be set up with a new direction, and its energy will be multiplied by the color of the surface that it travels through, and also multiplied by 1 minus the reflectance of the sphere that it's traveling through. With that concept, let's look at the code. Here we are in the code. I'm going to jump over to the shader, but just before I do that, I want to briefly take a look at a modification that I made to the spheres. By the way, this is all data oriented, so this might be a little painful to read because it's very verbose. I did my best. Here we have eta, and eta is the refractive index. We could simply encode a refractive index. For instance, the refractive index of glass is about 1.49 or something like that, and the refractive index of air is 1. GLSL's refract function deals with the ratio of the refractive index in over refractive index out. In the example of going from air to glass, that will be 1 over 1.49. And it doesn't matter exactly what that is. What I'm trying to get at is that I'm not doing a fully accurate refraction where we have a refraction on the incoming and outcoming ray to the object. I'm just doing a simple, like, comes in, bends once, that's it. So we always know that the medium will always be traveling from air into something, so it's always going to be 1 over something, and so this will be less than 1, always, whatever the quantity is. So what I'll do here is I'll actually take the reciprocal of this. So it's not actually the refractive index of the medium, it's actually the reciprocal of the refractive index. So if I take 1 over 1, that's 1, 1 over 2 is 0.5, and so I'll just put in anything between 0.5 to 1 is the range that I'll take for my refractive indices. With that out of the way, we should be good to go, and we'll go over to the shader now. So here we are in the shader. I know this is a little overwhelming. What I'll do is I'll just declare for the sphere the refractive index, and then it turned out that this won't really, what I wanted to do was take a vec3, but GLSL simply doesn't pad things that way, and so what I'll do, a little dodgy, but it does work. And now furthermore for this ray, I think we're ready to do this. I'm actually going to store the energy. I like to think of it as energy. You can think of it as a tint if you like. So I'm just going to store that inside the ray. And now I'll just search through, and anywhere I see, I think I call this ray energy, we don't need that. So here, ray energy, don't need it. At this point here, we're initializing this variable. I'm actually going to put that with the ray initialization stuff. There we go. Okay, and then if I look down here, I'm calling the scatter, again, because I'm inputting the ray. I don't need that variable basically. And then here, where I'm coloring, I will access the ray's energy, read the variable there. Same thing down here. This is a lot of fun. Okay, now what's the next? Okay, no worries. So I can just get rid of this completely, and I'll do the same thing here. And there we go. Okay, so probably a good idea just to run this and check that it is working. So I'll go to the raytracer.py, give that a go. No errors, so that's a good sign. And as we can see, we have the same scene as before. Excellent, so I'll close that down. And now I'm going to modify, or keep modifying this stuff. So I'll go down to the scatter, and I'm just going to get rid of, this stuff is fine, the geometric stuff, but I'm just going to, let's say, make a comment, we'll say the ray, yeah, sphere tints the ray. And what I'll do is modify the ray's energy. I'm just going to take it right back, keep it very simple. I won't even change the ray's direction. And at the moment, I will just return. So let me talk through this. So I know I've changed a few things. I'm trying to make it basic, build it up from there. So we look at the sphere that we are going to hit. We work out which position on the sphere we've hit. We work out the normal. And then all I do is I just tint the ray with the sphere's color and change its position. So it's still traveling in the same direction. It's just been tinted with the sphere's color. Now I'm returning black because this is the additive color, the way this is being used. If I look at the original function, the main function, we're traveling along and then we add that color. So I don't want this to really add any color. I just want it to tint the ray. So I'll give this a go. This is sort of cool. This is sort of artistic. We've got these rays, but these spheres, but they're see-through. It's like plastic circles. So the ray's just shooting directly through it. Okay, so now what I want to do is I want to calculate the refraction and use that to bend the light as it travels through the ray. Okay, so I'm going to call GLSL's refract function. We need to input the incident ray, which is the ray's direction, the normal vector that we're going to refract around, that was calculated up above, and then the refractive ratio, if you will. So now let's have a look at that. Okay, now things are sort of funky. Let's look at this yellow sphere in front of me. Looks like the world's upside down. As I get closer, it whoop, sort of flips around. We get some glassy effects. That's sort of cool. So at the moment, this is just the refraction. And we can get some pretty cool effects just this by itself. I'm pretty impressed with this. This would probably be a good point for me to mention that I'm not trying necessarily to make a photorealistic ray tracer, so much as just something that performs with reasonable speed, can be real time, and looks sort of cool. In addition to that, I want to add some reflection for the sky. Okay, so I'm going to take another copy of the ray, which is reflected around the sphere's normal, and this is where I'm going to get my sky reflection. I'm keeping it super basic at the moment. This is not going to look correct, but I think it's good just to see it. Let's see what that looks like. Super bright. Have a look at that. This is... oh, because every time the ray travels, it picks up another image of the sky, and that is additive. So, I mean, this does look sort of cool, but it's not correct. So what we can do is we can tint this according to the ray's energy. See what that looks like. And that is equally bad. Of course, as I was saying on paper, we need to make sure that this is energy conserving. And so what I'll do is I'll take the sphere's reflectance, okay? So that is the reflected amount, and then 1 minus that will be the transmitted amount. Now this is looking a lot better. It's not super bright as it was before. So looking at these spheres, we can see they have a portion of the sky reflected, and additionally, we can also see through them. Now, like I said on paper, this does produce some cool results, but it's not strictly physically accurate. The reflections coming off the sphere are not taking the other spheres into account. They're just looking at the sky. However, it's a great idea not to push ourselves too far, do too many things at once, and for that reason, I'm pretty happy with this for now. This is pretty cool. Okay, so that'll be it for now. Look, as I always say, thank you so much for watching. I hope you got something out of this, and happy coding. I'll see you again soon. Bye.